Okay, so let me start. So with a, I should take the other one. With a reminder, quick reminder from last time. We saw okay, the reminder. And I will just do a reminder about MPS because it's the main subject of today. So we saw that a generic state of a spin chain can be written like this. Where we have 2 to the n coefficients like this. And then we move to these tensor network notations where we forget the state and look only at its coefficients. And this thing we wrote like this, like a, if you like a blob like this. And the MPS on that was a guess for the form of this tensor. Okay, I guess like this. If we temporarily go back to the old-fashioned non-tensor notation, what this encapsulates is the fact that the state now depends on tensors or matrices, or say tuples of matrices. And for such a matrix product states with open boundary conditions, this means that this guy corresponds to a vector. It's A1 of I1. And now we have matrices, I2, 2. Okay, so, sorry, now it's, of course, I have states coefficients. Okay, so that's an MPS, either written in tensor network diagram or in old-fashioned way. And, okay, here typically this is from 1 to D, where this is the physical dimension. Okay, I hope at this stage you more or less remember. Now, why was it nice, this ansatz? Because it's, okay, I'm going to say here why it was nice. The ansatz is very nice because it's locally parametrized. And so we went from D to the N to essentially D squares times D times N parameters. So that's much less. So we're in a way happy about that. And it's also fully expressive. What that means is that by taking capital D large enough, the bond dimension large enough, you get everything. But so far, this statement that we saw of being fully expressive is in a way useless because it requires D of the order of dn over 2. So you see that it gives the same cost. Okay, if there is no magic. So if we want to represent any state like this, we pay the cost of an exponentially large bond dimension. And of course, we get the number of parameters we would have in a fully generic state. So, okay, but today, typically, we'll try to improve much more on this, say, in which cases we need, in fact, very small capital D, small bond dimension to get excellent approximations. And why it's convenient also is that it's efficiently computable. I think that's that's something that's crucial and sometimes a bit forgotten about such ansatz is that not only should they verify all the properties you want, but they should allow efficient computations of observables. And again, if a wave function, even if you know a wave function exactly, it doesn't follow that you know exactly a correlation function because it requires, in principle, summing 2 to the n coefficients, which can be impractical in practice. But what we saw is that this essentially takes this form. Of a ladder, okay, whereas the operator O appears here, and here essentially it's and A. And we remember that this is cheap because you can contract it essentially this way. And at this stage also, final point is that our intuition, why is that a good idea? We got only this intuition from the PEPS construction, okay, that this should be essentially weakly entangled and target the right corner of the Hilbert space. So the intuition from PEPS construction that it should be good. Okay. Okay, so that's all for the reminder. And today we want to know sort of why it works, really, but beyond the simple intuition, and how to find the best A, okay. How to find the coefficients of the state. So algorithms. Okay. Okay, so that should be from last time. And sadly, we have to start right away with a technical thing, a technical prerequisite. I suspect you are already familiar in one way or another with it, but it's going to be so central that I introduce it precisely. Technical, I would say aparté, but we didn't do much already. And it's the sin SVD. So sin singular value decomposition, which, as we'll see, is equivalent to the Schmidt decomposition. And it's going to be the central tool for us to show why MPS work and also how they can be optimized. So, so what is the, I will tell you on one side what is the SVD. Maybe I should write what it is first. Singular value decomposition. And I'll try to tell you on the other side what the Schmidt decomposition is, and it's the same. So you will see that it's exactly the same, simply written differently, and in the tensor notation, it's going to be clear. So if you have a certain matrix that is a rectangular matrix, n times m, you can write it U lambda V dag. And what is crucial is the size here are n times R times R times M. Lambda is diagonal with positive entries. And U, V are isometries. And so what this means is that U dagger is equal to the identity, and V dagger is also equal to the identity. No, sorry, I wrote it wrong. Obviously, it's the dagger is here. Okay, you have to verify that I am actually allowed to make this multiplication. Okay, these are rectangular matrices, and it's the identity. I put R, like it's the identity for matrices that are R by R. Okay, so for every matrix like this, you can do this decomposition. I will tell you just in a bit how you find it. But yeah, we'll see. It's a sort of generalization of the diagonalization. And there is another concept that we see quite often in quantum information, that's this Schmidt decomposition. And this Schmidt decomposition is, I give you a state that is that belongs to a tensor product space of two Hilbert spaces. And what you do is you find you write it. Sorry, some. So psi k left. Okay, where these states are orthogonal. So no, left, sorry, and same for right. Okay. And the lambda k are superior, larger, or equal to 0.
Yes. Here we assume something about A, so that all the coefficients of lambda are positive, right?
No, nothing. Nothing. So this is generic for whatever.
Because when you diagonalize a matrix.
So it's not diagonalization. Okay, it's really a different thing. We'll see in a second how it's related to diagonalization. But it's not straightforwardly. I should not have said it's a generalization of diagonalization. It's looks like diagonalization. It's related to the diagonalization of A dag A and A dag, which are square matrices. We'll see in a second. I just want to say, so now these are 2 points of view that are actually identical. These are the exact same operations if you reverse Brown-Ketz. Okay, a matrix, as we saw previously, I can write A like this. And what this singular value decomposition tells me is that now A is equal to something like this, where it's U lambda V dagger, okay? And what these relations tell us here is that U, okay, I shouldn't put it here, is that we have the extra condition that here it's U star, U. When we do this, it's equal to this, and V okay, I'm just writing down the fact that this relation here in tensor notation, okay? No. Yeah, here you're right. You're right. Here I should say here it's diagonal, but that's why I write it smaller. But there is no real convention for it. Okay, here it's really just a notation that to say the thing above, and indeed we should specify that here lambda is diagonal. Okay. But here, if you have psi, you see that psi lives in a tensor product space, so I can write the two legs corresponding to psi. And now if I do the Schmidt decomposition, essentially it tells me that it's psi, left. And now I sum over k with the lambda k. Okay, so it's like this. psi right. Okay. And likewise, we have the same relation for psi left and psi right from the fact that they are orthogonal. Okay, so this is this here gives me the equivalent thing that I saw there, which is sorry, this is psi left star psi left. And okay, so in fact it's just the same thing. Is there, you see every rectangular matrix you can actually see as the coefficient of the state in the tensor product space. And so this Schmidt decomposition that decomposes states is really equivalent to this decomposition of matrices. Sorry, like this is really a technical starting point, but we have to be very clear about the SVD because we are going to use it a lot. So just to tell you that in some cases it's natural to see it one way or another. And it's also to, in some way, test now your understanding of this tensor point of view where you don't care and you go from matrices to states on bigger spaces. Okay? So now how do you get that from the link with diagonalization? So if you already know how to diagonalize matrices, you are in a way, you're in business because what you can check is that A dag A is like V lambda U dag U lambda V dag. And so this is V lambda square V dag. And the same for A dag. Okay, both are actually square matrices, n times n and m times m. V. Okay. So basically, you can get the singular values from the squares of the the eigenvalues are the squares of the singular values. We are guaranteed here that they are positive because these are positive matrices, and you can also find the V and U matrices from the diagonalization. What we are going to do later is do it for arbitrary tensors, but it's just the same, okay? For arbitrary tensors, the SVD is going to be the tool that allows us to split a tensor in pieces. Okay, so if we have a tensor like this, what we can do is do its SVD by sort of deciding what is left and what is right here. Okay. And now the decomposition is like this. And this is really the kind of tool that is going to allow us to MPSize whatever state. Okay, you see that using the SVD, I can start to split things into tensors. And again, we have these isometry conditions like this. And like this. Okay, so here's it's if it's U V dag. Here it's U star U. Here like V star. Okay, later on I will try to encode these isometry conditions like this. So try to write in blues when things are isometries on the left side of a tensor, and in red when there are isometries on the right side. So in between it's going to be white usually, so we'll get French flags all along, okay? Okay, so this is done for this introduction to SVD, to general tensors. You will see that now, now that we have this tool, we can do a lot of manipulations to tensors. And we can show, now what I want to show is that states verifying the area law, so which we, as we discussed first, are a large class of interesting states we would want to have, verifying the area law, are well approximated by MPS. And that's what we are going to do now for the next, I don't know, hour maybe. No, a bit less probably. Okay. So now, just to insist, what we're going to do now is theory. What I'm going to do is not a practical algorithm, in the sense that I will assume we know the starting point. So that we have a starting point like this. This is the state. Okay, I'll just put IN. We have an initial state like this, and what I want to do is write it as an MPS, but in a better way than what I did last time, when I just regrouped the legs in a kind of cheating way. Now what I want to do is use the SVD that we just learned to truncate it, to write it as an MPS. So the first is I am going to cut it like this, do an SVD here. What this gives me, so here, yeah, really the argument is just SVD. And so we have like U1, lambda 1, and V1 DAG. And they verify, they are, if you like, blue here and red here. Okay, so that's the first step.
Do the colors have any particular meaning?
Yes, this meaning here. I will write in blue things that when you contract them like this, with their adjoint, they give the identity. And this, when you close them on the other side. So that's just from the SVD, basically, the fact that there are isometries. You will see, I mean, it's not crucial, but later it's sort of a way to confirm that we have the right form for our states. Okay, so now we will want to then, if you like, do the SVD of the block here. Okay, then it will itself split. Then we split, and then this will get the form of an MPS. But we want to be slightly more careful than that, because what I will want is that the lambdas here can always be interpreted as the Schmidt values of the state, so that everywhere I cut, these lambdas correspond to the lambda in the Schmidt decomposition for that cut. This way it ensures that this guy will have a good entanglement interpretation. So in fact, I should not, okay, you will see, we sort of see after the fact why it was the right way to do it. Here, I will first fuse the singular values with the right part. So like fuse lambda 1 and V1, one DAG, and then SVD. So if you like, now I have something like this. This one is still U1, and this is a V1 tilde dagger. And now it's not whoa. It's not red because it's no longer an isometry. And this I cut. I cut again. With an SVD. And what I get now is that I have something like this. So now this is an isometry, this is also an isometry, and this is an isometry. And we anticipate a little bit again on what will come next by here we will want to reinsert the lambda 1 here. Okay, if I just kept on like this, I would get something that's in an MPS, but not exactly in the most general canonical form I would like. So here I just insert lambda 1, lambda minus 1. Okay, right now it may look a bit weird why we do this. So these steps of fusion of the eigenvalues are maybe the ones that are not natural. They are just to get an MPS in a specially convenient form. But the crucial step is that we take SVDs. Okay, that's really the part. Okay, that's not what I should have done. Sorry. So what I did here is that I have U1, now lambda 1 minus 1, U2. Okay, so I just inserted a resolution of the identity here. And now what I will do is just regroup this into one tensor. And after this regrouping, now what we have is something like this. Where this is U1, this is lambda 1, this is gamma 2, the central matrix has no property, no special property. Okay, we arrived at this. This is now where we are going to say, okay, let's do it n times. At this stage, we can use induction to say we keep on, okay, we do it n, okay, maybe n minus 2 more times, and we get a state like this. One, two, three, four, five. Okay. And in this state, only the first and last ones are isometries. But what is crucial is that now you see it's an MPS. So by doing, here it's U1, lambda 2, so by successively doing this singular value decomposition every time to the next block, we arrive at a state here that takes the form of an MPS. At this stage, in fact, it's not better than what I did last time. So for a generic state, this is not better. For a generic state, why is it not better? Because, okay, we have to count how many singular values we have generically every time. So here, we can see that lambda 1 has d coefficients. Okay, it's small d by small, like d by d, because here it's a leg that has size d. But now when I do the SVD here, I have d here and d here. So now lambda 2 has d squared coefficients. And in the same way, the number of coefficients in lambda is gonna be maxed out in the middle. So it's essentially lambda n over 2 is gonna have d n over 2 coefficients. And so, strictly speaking, we are not fully better, than last time. And so we have, for a generic state, we have an MPS, but this MPS form here has a huge bond dimension, still exponential bond dimension. What we want to do now, I think quite naturally, is we will want to truncate these singular values, order them by decreasing order, and then cut at some point. And what we hope is that we still keep a good approximation. For a generic state, we don't. These singular values don't have to decay fast. But for states of interest, they will decay fast. Why? Because they are related to entanglement. And so if they decay slowly, the state would be strongly entangled. And that's essentially the core of the argument. Like a state that is weakly entangled has quickly decaying singular values, whereas a state that is strongly entangled has slowly decaying singular values, and thus is not well approximated by an MPS. So I will just show that a tiny bit more formally, that these... and this is where being annoying with like all this repackaging on which side do I put the lambdas and is going to be important, is to see the link with entanglement entropy. I don't know where I do it. Maybe here. So the link with entanglement. So the first step, we'll see. Singular values are related. These singular values here are related to the quality of approximation if I truncate, and they are also related to the. They are also related with entanglement. So I start by showing the link with entanglement. We start. So there is my state from here that I wrote in this form. And now let's say I decide to look at the entanglement entropy between two sides of the chain. I call that the region R and that the region R complement. And I want to know what is the entanglement between these two regions as the function of this expression of the state. And what you see is that for that we have to write rho R, which is the trace over RC of these states. And what form does it take? In tensor network notation, it's pretty easy. This is the expression for R here, for rho R, sorry. So I take the bra, the ket here, the bra here, and I trace the degrees of freedom here, which means I contract here the degrees of freedom. And now rho R is indeed a matrix acting on the Hilbert space of this side, so it's something that has two legs and two legs here, I mean, at least we agree about the dimensionality. This is now that we are going to use what we did before. What can we say about this block of states here? This tensor here, at some point in the steps that we did here, it corresponded to a red block. This is something that is right of a singular value. So this thing, these two tensors here, these are isometries. Right? From the way we proceeded to construct the state, when we stopped at this singular value here, what remains here, no matter what we did to it after, because it was exact, this is an isometry. So now this means that the rho is just equal to this. And now we have this, okay? We can contract for free all this part because it's just an isometry. Maybe I should have used red, like it's actually, all this block here is an isometry. But now, what is also crucial is that this guy here is an isometry. If you remember, always the left guy is an isometry. And before we took the lambda out, this is also an isometry. And this is also an isometry. So what this means is that now the state, essentially, rho r is a certain isometry with two legs, my lambdas, and another isometry. Okay. Check it's U. Okay. And so what this tells us, okay, maybe I should have put one in red actually. Okay, this is not very, anyway. So essentially here, this is the diagonalization of rho, you see? And so now what, we'll use another board, but essentially we have identified the fact that the lambdas, and this is the crucial part, no matter where I cut this chain, the lambdas, the singular values at the point where I cut, correspond to the Schmidt values. Okay, this corresponds to the eigenvalues of rho. Okay, their squares correspond to the eigenvalues of rho. Again, no matter where I cut, that's what is crucial in a way in this formulation. So now if we, for example, want to write, I don't know what we could ask, like for a measure of entanglement, let's look at the entanglement entropy across this cut, the Renyi entropy for this region. Well, now it's just the sum over I equal 1 to d to the k. Okay, in principle, we have, if it's cut at bond k, we have d to the k. 1 over 1 minus alpha. No, sorry, it's I. Okay, so the entanglement entropy between the two sides of the chain, Renyi or von Neumann entropy, you get it just from the singular values that are stored in the state here. So this is just to say that these lambdas, these singular values, are related to entanglement. And the second step is to see that they are related to truncation error. So now truncation error. Now I will write my state. I will write a Schmidt decomposition of my state, a generic one. Say again d to the k. Oh, sorry. Oh, I was not smart. Okay. So I take a generic state and I cut it. I do its Schmidt decomposition on two parts of the chain. And now I look at psi truncated. Which is the same state, but now I truncate the singular values at a certain level. It's the same. Well, what you see in that case is that the norm, the difference between psi and the truncated version are just the sum of the squares of the singular values beyond where you cut. Actually, here it's I. Okay, so this is a fairly trivial statement. That is, if I cut singular values, the error I make in the fidelity between my state and the one where I truncated a bond is given by the singular values I didn't take. And this is really the argument. Okay, so now I will maybe explain. Yes.
I didn't get what the
Sorry, where?
with the
Yes, again, where's the?
with the prism.
This is the density matrix in region R.
Okay.
So it corresponds to the connection here means I trace on the right side. I trace the right Hilbert space, and of course I keep open legs on the side where rho R is defined. And then, because I wrote the state initially in this form that we struggled to get with SVDs, there are specific properties such that these are isometries, these two blocks here. So when I contract them, it's just a line. And then the rest on the left of these singular values just here is also an isometry. So at the end, I have for free a diagonalization of the density matrix. That's what I wanted to show. And once I have this diagonalization of the density matrix, I just see that, for example, whatever entanglement measure entropy I compute is going to depend on these lambdas on the site where I cut. Again, no matter where I cut, that's what's nice with this thing. I have different lambda matrices, but if I cut around between two sites, the entanglement is encoded in these singular values. That's why we did all this tedious work in a way. And we see a second application of this, a second impact of the singular values is the fact that they control the error I make between the exact state and a state in which I would have truncated these singular values. Okay, like if I want to reduce the dimension here, I can just decide to truncate the singular values so that now it's not an MPS with exponential bond dimension, but something small, manageable in the computer. And in that case, the error I make is the sum of the singular values I didn't keep. And this is, again, because singular values have this interpretation from the Schmidt decomposition. Yeah, I might have messed up. So I wanted to use K for I cut at the bond K.
Okay, so it's the minimum between the two sides. Minimum.
Yeah, in a way. Yeah, you're right. So I imagine K is much smaller than n minus K.
Okay,
Yeah, you're right. It's of course.
You cut closer to that side.
Exactly. Yeah. You're right. K is the smallest of the two sides in a way. Very good. And now, so you have sort of two situations, okay? I'm just writing a bit more formally what I advertised at the beginning. You have two situations. So this is your singular values, lambda I, and this is I. And the favorable case is when they decay super fast, and you have here, something that is very close to 0, maybe 10 minus 10, like to machine precision, you don't see the difference. And your D that you can put on your computer is here. And here it's something large, okay, D to the K. In principle, there is a huge difference here, okay, between these two. So like, it's if you have fast decay, as a result, you have low entanglement. Okay, because if singular values decay fast, all quantities of that form will be small. Okay? And so you have good MPS approx. And the other case is if the singular values don't decay, or decay slower, something like this, I don't know. And you see that, yeah, I mean, all this region is what we lose by truncating. It's all the error in the fidelity. And here, okay, it's maybe tiny. And here, okay, like slow decay. But this implies, the slow decay implies large entanglement. And bad MPS approximation. So now this is, you see, this is a very, what I'm doing is a bit of an informal argument. I'm saying, okay, if this tail is large, it means that necessarily this is large. Okay, and so for states that have low entanglement, necessarily the tail is small. And so I make a good approximation. This is an argument that you should make more precise, but it gets technical, okay, like to really quantify precisely. But fortunately, it was made precise, this argument by Verstraete and Sirac. Let me check in what year, maybe in 2005 or approximately. So, you know, they just use this kind of argument that relating singular values and the entanglement and truncation. Again, so it's Sirac and Verstraete in 2005. What they show is that for Rényi entropies with alpha between 0 and 1, what you consider is you consider a psi minus psi d. And psi d here is a psi where all the bonds were cut to d, to a capital D. All the singular values on every single bond were cut. And what they show is that the norm of this cannot be too large. So it's 2, okay, I will n minus 1. I rewrite it a bit my way, a certain constant depending on alpha, exponential minus. Okay, so that's what they show. I have to explain a tiny bit. So this is the maximum Rényi entropy of a cut. Like of all the possible cuts, you know. This is a constant that depends on alpha. It's like a function of alpha, just a function of alpha, not of the rest. And this is essentially system size. So we still have that the error we make in terms of fidelity increases with system size, but only linearly. So essentially, that's a very, very good, very good bound. And if this Rényi entropy for a certain alpha is finite, this max, then this is what dominates the convergence. So it's a power law convergence as a function of the bond dimension. So if states essentially have finite Rényi entropy, we know that the that the approximation is good, and it's quantified by this formula. Is that clear at this stage? This is, there are still assumptions. There are still the assumption that the states we care about have low Rényi entropy. That's absolutely not obvious. So this is Sirac-Verstraete 2005. And also, this is a statement that has the drawback that it talks about global properties of the state. And so we have the fact that this error increases linearly in n, but in a way that's errors always increase because of the infrared catastrophe when you make the system large in terms of fidelity. But that doesn't mean that the error on anything you measure is going to have this problem. And in particular, for local observable, we'll see it doesn't depend on n. So this was connected to physics in a way by Hastings in 2007. And Hastings basically showed the area law. So he showed that if you are in 1D and you have a local gapped Hamiltonian, then you have two things. You have area law for von Neumann entropy. And you have good MPS approximation. So weirdly, you could imagine that you just prove the area law, and then you use an argument like the one of Verstraete and Sirac to prove that since you have the area law, you have good approximation. But actually, Hastings proved von Neumann entropy, and von Neumann entropy is exactly equal one case, so that doesn't work. But sort of his argument can be used, and he used it to directly also that you have good MPS approximation. But you can use then an argument from Yi-Shen Yang from 2014, who showed that the same hypothesis imply area law for Rényi entropy as well. And then it allowed him to prove a better approximation result, which is for local observables. So you have this, where your psi here is a state of low energy state of a local Hamiltonian, and you compare with your MPS truncation of this state. And what you see, what you see is that this is a big O of 1 over d 1 minus alpha over 4 alpha. So for all alpha. Okay, I mean, I could have put anything here, but these alpha are related to the Rényi entropies. But essentially, you see that two things. This error we make for local observables doesn't depend on n, on the size of the system. And it's also for all alpha. So here, if you take alpha very close to 0, you get that the error decreases faster than any polynomial in the bond dimension. So this gives super polynomial convergence of local errors. This is not quite exponential, but and super polynomial convergence is I would say already a miracle, okay, in terms of what you can expect. No, I will keep this aside. All right, so all of these are essentially making this argument more formal and adding some extra physics to get from locality and a gap the fact that entanglement is limited in these systems. Okay, so now we can. This is enough for the purely theoretical part. now we are going to see, of course, how we find the best MPS representation for a certain state. Because you have to see that here, we completely cheated. So we assume we are given the state. Then we do these SVDs of exponentially large, actually, systems that are completely unfeasible on the computer because this is exponentially large. And assuming all this can be done, then we say, OK, this MPS can be made, by truncating this MPS, we make a very small error. So the state has a good MPS representation. But this is not a practical algorithm at all. Okay? So now we're going to move to the algorithms. I should say also that this is the slight cheating part there is in these theorems here, is that here they assume that to get these errors that you can get a good, that you can find this MPS representation. It's really, there exists a good truncation, a good MPS representation of the state that has small error. It doesn't tell you that you can find it efficiently. Then there are algorithms that in practice find these representations efficiently, but usually it's not proved that they converge quickly, or you could still in principle have a state that is well approximable by MPS, but that in practice you don't find it numerically. This is left open by these theorems. I should say in practice it doesn't happen, so we are fine. Like the algorithm converge, but essentially it's an optimization problem to find it's a non-convex optimization problem to find the best MPS representation. And so in general it's difficult. Okay, so there are two things we will want to do today for algorithms. We'll want to find the ground state. So find argmin find the state that minimizes the energy. And we will also do another thing, which is can be very useful in practice, is solve the Schrödinger equation. So solve okay. So there are the two things we can easily do with tensor networks. And for that, I will show you practical. This we will do with DMRG. And this we will do with an algorithm called TBD. I will just say later what it means. But before starting and giving these algorithms, these algorithms have the property that they are very easy to implement in tensor network form, but they are not necessarily the most principled in a general conceptual, from a conceptual point of view. And on the other hand, there are other algorithms that are more geometric, more principled, but that are more difficult to implement nicely in tensor network form, although they are doable. So what I will do is these ones I will really explain well in tensor network form. And just before, I want to tell you quickly what is a way I like, sort of the principled way, in my opinion, to solve these two problems. And it can be done this way, but it's a bit more difficult. And this idea is what people call the time-dependent variational principle. So here, I'm going to be at the level of heuristics. And if you're interested, you can always find it in the literature. And the idea that these approaches use is the fact that we have the Hilbert space in which we have a submanifold that are, that maybe I can call M, that is our MPS of a certain bond dimension. And we have a point inside this manifold is just a certain MPS. And what you can do is there is a natural notion of distance of states in this MPS that is just the one induced by the distance on the Hilbert space. Okay, this manifold is a subspace of the Hilbert space. You can use the Hilbert norm to give a norm on states in the manifold. And in particular, if we want to be slightly fancy, if you take a point and the tangent space on this point, this allows you, you have tangent vectors. You can use as a metric for this tangent vector the Hilbert space scalar product here. So you can use the natural notion of metric on the manifold, the metric simply induced by the global metric on the full Hilbert space. So basically you take as metric on the manifold the one induced by the scalar product on H. What I would like to insist, and this is why these approaches are, in a way, they look like doing gradient descent on this, but they are slightly more subtle than that because this is very, very different, this metric, from the Euclidean metric on the coefficients. Okay, so your state contains coefficients that are sort of tensors. What you could do is just take the L2 norm of this coefficient, sum the squares of your coefficient and declare that this is kind of the norm, okay, in here. But of course, this is a very, very different norm. I mean, if I wiggle A little, for some coefficients, the state moves a lot in Hilbert space. For some, it doesn't move at all, okay? And it turns out using this one is, of course, much better than using this one. But when I say much better, it's sometimes by 5 orders of magnitude better. Okay, and so really this is the geometry you have to use on this state. And then these two things here are very easy to do geometrically. So say, now, okay, I will actually do it on the right, sorry. The first, finding the minimum, you can do by Riemannian gradient descent. And Riemannian gradient descent is just gradient descent where you take into account the fact that the space on which you are has a non-trivial, non-Euclidean metric. And this is important because the notion of steep, so gradient descent, you're doing steepest descent, okay? The notion of steep is metric dependent. It's not defined independently of the metric. So for one, what you do is Riemannian gradient descent or some refinement, okay, some quasi-Newton method. You do Riemannian gradient descent, and that finds very quickly the minimum. So that's a very efficient way. And for 2, I don't know if that's well, for 2, the difficulty in solving the Schrödinger equation is that if psi is a state in the manifold, this is no longer a state in the manifold. If you add this is whatever in principle, this extra term you add. But what you can do is project this on the tangent space at the point where you are and move the state a little bit in the direction of the tangent space. So essentially what you do is dt psi equals minus I p h psi, where this is the tangent space projector. And this is something that's going to depend on the metric, and you have to be careful geometrically how you define it, but heuristically, at least it's pretty clear, okay? You move a little bit and you project. Move a little bit, you project to the manifold, to the tangent space projector. Okay, and so this, I would say, is the principled way to do it, or it's a way that is that has a great advantage that it is completely general. Okay, this works, I would say, for everything, even if you don't have tensor networks. Okay, so whatever actually ansatz wave function you have, you can apply these kinds of ideas, and it works. So that's a fairly general method. But we'll see, in fact, more specialized techniques that have the advantage that they are simpler to implement, and that they also take advantage of the kind of technology we just developed to prove that that states are well approximated by MPS. Sadly, there is another technical aparté we have to do before getting there. I guess I will do that, and then we'll do a break. Maybe other questions at this stage? Again, I stay at the level of words. I can give you a pointer to the literature if you want to implement that. The drawback of these methods is that implementing this is slightly more complicated when you write it in tensor network form. But crucially, it can still all be done without ever an exponential cost. It's still something that can be done fully in compressed representation. So there is no cheating. So now what I want to show you is I want to sort of this is the last step before proper algorithms, is to get MPS in canonical form without cheating. Canonical form without cheating. Okay, you saw that before. Sadly, I erased it, but our MPS, it's okay, a general MPS has this form. And what I want to show is that you can always write it this way. Without any loss of generality. And when I mean this way, really with the same properties as before, that here this is an isometry, here also, here also, and that in between we have singular values, gamma 2. Okay, so this is not totally obvious. This form is so convenient, as we saw already, to prove things. It turns out it's also extremely convenient to optimize the MPS. And so if we have an MPS in this form, we would like to show that in general we can put it in this form. And why is that the case? I mean, the main thing we are going to use is this thing called gauge freedom. And that maybe you were wondering, or maybe you noted it already, that the map A gives psi A, that to a tensor associate the states we construct with it is not injective. And that's fairly easy to see if you take something like this with A1, A2. I just zoomed on a small part of the MPS, where this is equal to the same where you inserted here a matrix and its inverse. Okay, this is clearly the same tensor here. But now what I can do is choose to group like this. And this gives me a new MPS representation, where here I have B1 and B2. Okay, so it's not injective, the map. And we can use this type of freedom precisely to change an MPS in arbitrary form to this special form. How would we do it? That's we could do like before, you know, intuitively. Before we had a general state, and we had put it in canonical forms through successive SVDs. Okay, I'll let you digest this already. Yeah.
You're saying that you can change basis, and that's what you mean by distributed freedom? Or
So here it's not really a change of basis. It's in the auxiliary space, if you like. Yeah, but so I insert this thing that is essentially that is the identity, so it doesn't change the state, and now I regroup. And so the elementary tensors are different, but the full state is the same for sure. Yeah, exactly. Yeah. Okay, so to put it in canonical form, we could just see this thing as just a special case of a generic. We could just see that this guy is just this, you know, and apply the same singular value decomposition trick with reshuffling of the lambdas to get this. But that's not allowed because, as I told you before, this is not an algorithm. This is not a practical algorithm because it has an exponential cost, this transformation from this to this. So we somehow have to use this strategy of doing successive singular value decomposition without ever calling routines that involve many legs at the same time in a way that would have an exponential cost. You see? So, but it turns out that because the singular value decomposition is related to the diagonalization, we can in fact get everything we want just by only ever doing diagonalization of the small thing of the two. This is what I am going to try to show. So now I start with an MPS. Let's give it 5 legs. And the first step to put it in this canonical form is to do the SVD. Okay, if you remember, I will want to SVD here. But the problem is that this singular value decomposition would spit out a V. Okay, I should say, in these drawings, you will have to assume already here that there are a ton of legs, okay, not just 4. I draw 4 for convenience. 4 would still fit on a computer, but imagine it's a very long chain. So I can't do the SVD here, at least naively, because this V is huge. But at least I can know the U of the singular value. Why? Because I can define a row that is just this. Sorry. So I defined a row that is like before, the row for the part here. But this I contract. It's a ladder. It's cheap. So this is equal to this. Okay? But this is also, now I recontract, so this is this. Okay, all these steps are doable efficiently on the computer without crazy cost, okay, like without more than d cube cost here. But now I can diagonalize, so this is equal to u lambda square u. And so what this tells me is that the original state the original MPS is now equal to Okay? Except, so what I should just really insist, what I know and what I don't know, okay? So if you like, I should have taken the same form. And so here, I know lambda, I know u, but I don't know v. This is, okay? But what this step of contracting, of writing the density matrix, contracting, and then diagonalizing does is give me this u here, okay? But it doesn't give me this v. But this is where I can be smart. Is that how can I express v dagger here? Well, if I apply u minus 1 here, lambda minus 1, I will get that v dag is equal to, okay, I should write it. If now I, is that clear? So I know u and lambda. V I don't know, but I can just multiply by u dag and lambda minus 1 here. And so I get that v is equal to this. But here I know everything, and this is a compact tensor form. So now what I'm going to do, so if you remember, I have to, what I care about at the end is lambda. I have to reinsert the lambda here. So actually what I will use is, now I put the lambda back here, so now it goes away here. Okay? And this is this object that I will now SVD. How do I, this is what I want to SVD again, okay, to get the canonical form. I SVD here. Well, this is like SVDing here, okay? Same problem as before. In principle here it's very large. But what I will do is SVD here in the same way I did here by first constructing a density matrix. Diagonalizing it is going to give me the u and the lambda. Then what is going to remain is the v, but this v I can express as a function of the other side. And if I keep on, no step is going to be expansive here. So in fact, here we don't exactly probably yet see why it stays cheap. One should probably go to the second stage to see why it stays cheap. I think yeah, okay, maybe let me just show that getting the yeah. Do you need to see the next step, or is it roughly clear that I can iterate?
The idea that you never pay more than the bound dimension.
Yes. Okay. I think at this stage, since we only did one here, it seems that it grows. Okay. So what I want to show, okay, I should show it actually, because what is crucial is that it's going to go to 2 on the left side, but never more. Okay. So now we define again our row. Okay, to go to the next step. Yes, that's it. No. Yes, that's it. Okay. So again, like before, you contract like this. This is now, after the same steps as before, this is an object like this. Sorry, like this. And now you diagonalize. And it's written like this, after diagonalization. And here it's giving you U2 dag, and lambda 2 squared. And so like before, we have that yeah. So what this tells us is that this is equal to but again, this one is unknown, okay, in our decomposition. And this is what we found, and this is what we found here. And here it was what I had called before V1 tilde dag. Okay, so by diagonalizing the density matrix, I get one part of the singular value decomposition of this matrix here. Okay. Well, what we know is that this guy is equal to this. Okay? And so what we can now do is do as before. We apply U2 dagger here. And now this is equal to and this is precisely the thing I will want to diagonalize at the next step. But now it's written this way. This is again a tensor that is cheap. And you see that the number of legs is again gone back here to 1. And so every time the number of legs here is not going to explode. Yeah, my number of leg matches, so I'm happy. Okay, so this is slightly non-trivial, but it is to not lie to you in a way, like really show that these things, now actually we have an algorithm that we take an MPS, we do this succession of steps. None of them is expensive in the sense that none of them has an exponential cost. All of them have cost d cube, actually. At most d cube, and at the end, we get an MPS in canonical form. So later on, we can assume that we work with MPS in canonical form. We're not gonna lose any generality. Okay. We could start in the first place for MPS in canonical form. And if our MPS is not in canonical form, well, we could run this algorithm and put it in canonical form. Okay. Okay? Just let me show you. So this form is called canonical form. This form like this. And okay, I say it's an MPS. If you're really a purist, you could say you didn't allow beforehand that there are matrices in between. But now what we can do is regroup them. And if you remember the way they are constructed, depending on the way you regroup them, you're going to get different properties. So first, okay, so these are the ends. Now we can, this is the canonical form, the starting point, so canonical. what you can do is now group the left singular value with the matrix, with the tensor on its right. Okay. And this is going to give a new MPS. I mean, not the same MPS, but with a different parametrization. And what you can convince yourself of is that now all of these are blue, in a way. So if you group them like this, all are isometries to the left except the last one. Okay, because the last one was a right isometry, but now we put the singular values. And there is no way, of course, that they are all isometries. We'll see. It would give trivial expectation values. Another option to regroup is to regroup the other way. So now you group like this. And this will give a state where now everything is red but the last one. Okay, sometimes I think this is called left canonical or left orthogonal. And finally, you can do a different regrouping, which is the one that is going to be the most useful for us, that I hope I will not mess up, which is group like this. That on the left, you group such as to get something left canonical, and on the right, okay, I should probably add one side for it to be not trivial. You group like this. And then the final one, in the middle, you group like this. And this is going to give a state where you have blue, blue, and here red, red. And only the center site is not an isometry. Okay, why is this? This is called mixed canonical. So you see, what is cool with this original canonical form is that once we have it, by regrouping tensors together, we can get isometries either all on the left, all on the right, or on the left and on the right of a certain center site. And why is it? One thing it's convenient for example, is that if you want to compute expectation values, expectations, what happens is that psi, a certain operator psi, you know, if you remember, this is a ladder. But let's say you are smart and you compute it, you put yourself in mixed canonical form, such that the operator you contract is just on the center site. Well, by using the isometry properties, now you don't even have to contract the ladder. In a way, this contraction is straightforward, and it's this. Sorry. Okay, so that does instantly the contraction for you. So that's one of the use of this canonical form, and another is that I wouldn't say that's the main use. We'll see in the algorithm what's the main interest. And finally, it's good for it's good as we saw before, but for approximation or for compression rather. So if you have an MPS that is whatever, and it has a certain bond dimension d large, maybe too large, maybe you want to reduce it. Well, what you do is you put it in canonical form. And then you truncate the lambdas to d tilde small. Okay, and you see in some sense it's for each bipartition, this is the best cut, okay, to do this. So if you had an MPS like this with a bond dimension that is large, it's absolutely unclear how to kill some coefficients to get a sparser representation. But once you put in canonical form, the prescription is very clear. Just look at all the singular values here, order them, and kill the ones that are the smallest up to a certain threshold, and get a smaller thing. So this canonical form allows us to visually, instantly compress a matrix product state that would have a bond dimension that is too large. Okay, I think we stop for a short break now, maybe if you